Hello, so this is the next subtopic we are doing. Probably this is the fifth video recording that I'm doing. The next topic is Mayerhofs analysis. It's a very small topic. Just like the Zagis analysis, this is another way to analyze the bearing capacity failure or failure in the foundation due to insufficient bearing capacity. Okay, now this particular theory was proposed in 1951 by Mayerhofs. Okay, and this is applied for rough, shallow and deep foundations. So if we try to recollect the Zagis analysis, it was not for deep foundations. Okay, now assuming that logarithmic failure surface ends at the ground surface. Okay, so if you realize, if you can see, the curved surfaces are reaching near the ground level. Alright, this was not happening in case of the Zagis analysis. The Zagis analysis, the surface would end in the base of the foundation. Okay, so there are some very small differences between the two. Okay, so assuming that the logarithmic failure surface ends at the ground surface, and as such, he took into account the resistance offered by soil and surface of the footing above the base level of the foundation. Right? Now let's try to analyze. Now if you look at this diagram, whatever is on this side is Mayerhofs theory, what is on the other side is the Zagis theory, which we have already covered. Okay, so more or less same. Only thing what is happening, the failure surfaces, logarithmic surfaces are going way much above the foundation level. So where is the foundation level? This dotted line is a foundation level. Okay, now ABD, this triangular wedge, is the elastic triangular wedge. It's under elastic equilibrium. What is elastic equilibrium? Elastic equilibrium is this particular wedge of soil will be behaving as if it is monolithic with the foundation. It will be moving only vertically downward. There will be no laterally outward movement of this particular wedge. Alright? Then B, D, E. Can you see this? This entire portion is the radial shear zone, with DE being an arc of logarithmic spiral. So this, if you see this particular curve DE, it starts with very minor radius. The radius here is much smaller as compared to the radius here. That's a logarithmic spiral. The equation will be logarithmic for this particular curve. Okay, so now DE is an arc of logarithmic spiral, and BEFG, okay, is a mixed shear zone in which the shear varies between limits of radial and plane shear depending on the depth and roughness of foundation. Okay, so based on how deep your foundation is laid, then entire this curvature in some places might even look like as if it's a linear curve. I mean, it's a line. Okay, so that depends on how deep is your foundation, what is the roughness of the foundation. Alright, BD failure surface is considered. Where is BD? This is BD. Okay, and its inclination is considered this angle. Okay, ABD. This angle is considered to be 45 plus phi by 2, where phi is the angle of friction. Okay, so this angle ABD will be 45 plus phi by 2 with the horizontal. Okay, which is followed by logarithmic spiral, which extends near the ground surface. Okay, now if you look here, you have this P naught and S naught. If you see, the direction of P naught is normal to BF, and direction of S naught is along BF. So what are these P naught and S naught? P naught will be the normal stress, and S naught is the tangential stress. In other words, we also call it shear stress, which is acting on BF. In this particular case, it is acting on BF. Alright, so P naught and S naught are normal and tangential stresses. The superposition method is used to determine contribution of cohesion C, P naught, phi and gamma on ultimate bearing capacity, which we denote as Q suffix F. Okay. Following are ultimate bearing capacity equations considering shape, depth and inclination factor. Now the parent equation is this. Okay. Parent equation is just this is supposed to be QF. Okay. The parent equation is this. For particular cases, in case of vertical load, this equation gets modified into this, and the same equation for inclined load is modified slightly. Now, what is the modification? In this case, you will, when the loads are vertical, you won't find IC and I gamma. Okay, when the loads are inclined, you are not finding SC. So there will be slight changes. What is NC, NQ and gamma? These are bearing capacity factors. Now this NC, NQ and gamma, the equations governing are also given by Mayerhofs. Okay, and at the end of the presentation we will see that they are tabulated for various values of phi. You can clearly see the function of phi. Phi changes, the value of these factors will change. Correct? Everything entirely they are dependent on only phi. So there is a tabular column wherein you will have one column of phi and then corresponding NC, NQ and gamma factors. Okay. Now coming to this SC, IC and DC factors. Now what is SC, IC, DC? SC, SQ, S gamma, these are shape factors. IQ, IC, I gamma are inclination factors. Okay. For the load inclined at an angle 0 to vertical. Okay, so this is not 0, this is theta to vertical, or in your basic Punya the angle will be alpha to vertical. Okay, then DQ, DC, D gamma are depth factors. Okay, gamma dash is effective unit weight of soil above the base level of foundation. Gamma is the effective unit weight of soil below the foundation base. D is the depth of foundation. Kp is given as 10 squared 45 plus 5 by 2. What is this Kp? It is passive pressure coefficient. Okay. Now wherever you are going to input this value phi, you are not going to put any sign. Okay, it's just the value that is going to come, no positive, negative. Is the width of footing. Okay, and D will be the depth of footing. D is the depth of footing. Alright. The shape factors, these are given by Mayerhofs. Various equations are mentioned here. Okay. Alpha is the inclination of the load, inclination angle of resultant measured from vertical axis. Kp is the passive pressure coefficient. Okay, rest of things I have already explained before. Okay, the equation proposed by Mayerhofs to calculate phi for plane strain in terms of phi of triaxial will be given as 1.1 minus 0.1 b by n into phi triaxial. Right? And this is the finite tabular column wherein Mayerhofs bearing capacity factors are tabulated for various values of phi. In case the value of phi which is given to you maybe in your problem is somewhere in between, then you need to interpolate. Okay. Now coming to the end, I want you all to answer these two questions. Compare the bearing capacity factors proposed by Terzaghi and Mayerhofs and what is Kp. These two questions I want you all to answer. Okay, these are the references. Okay, the main presentation more or less I have taken from this presentation which is available on SlideShare. Okay, and a lot of content I have taken from NPTEL and basic English. Alright, okay, stay at home, don't roam around. I know you all will be losing your patience now, but still somehow you will have to bear it. Okay, till government announces has to be in green zone, don't move out. Alright, stay at home, study well, you are not posting any problems, so I'm just assuming that you are understanding everything. Alright. Also, if you have any question papers and you want any answers, so far I have been only covering theory, so anything related to theory questions. Once I start solving problems, maybe I can post problems that have come in Goa University question papers. Alright, so if you have anything, you can text it to me on my phone number. Your class representative will have it. Yes? Thank you. Stay safe. Bye. Hi, today we are going to do the next topic, that is effect of water table on bearing capacity. Okay, now what I have preferred is this NPTEL notes which are available free. Only thing, I have done some changes with respect to the terms that are used. Okay, so for ultimate bearing capacity, if I'm not mistaken, they are using QU, whereas we have so far been using QF. So I've done some editing on the same text. However, the main original source of all this is NPTEL. Okay, now before I start with this, let me tell you there is a lot of difference between what I'm going to cover now and what is mentioned in your textbooks. Okay, they're following different methods to identify the effect of water table. There are some 3 odd methods that are given in your textbooks, but when I referred these notes, I found them the most simplest. If you all want, you all are free to go with those methods. Absolutely no issues. Okay. Okay. Alright. So before I start, you guys need to revise a little bit of the Zagis analysis, because I'm going to explain everything in terms of the Zagis equation. Okay, the equation for ultimate bearing capacity given by Terzaghi is QF is equal to CNC gamma dF NQ plus 0.5 gamma B into N gamma. Alright, fine. Now the same equation can be given in multiple different ways based on which theory you are adopting. For example, we have so far only covered Terzaghi and Mayerhofs. If I am not mistaken, these are the only 2 theories that are there in your syllabus. But there are multiple more. There is Hansen's theory, there is Kempton's. Okay, so the equation might have slight changes. But whatever will be the effect of water table, the way this effect is incorporated in these various equations given by multiple people is same. The changes that you are going to do in the equation are irrespective of equation. What I am trying to say is, because of the presence of water table, primarily this gamma is going to change. What is gamma? Unit weight, right? So when there is water in the soil, otherwise usually we designate unit weight as gamma, that is bulk density. When the water will change, it can go to partial saturation, it can go to complete saturation. So you may designate this as gamma sat. Okay, if the water table is rising at a very high level, then you may even designate this as gamma prime or gamma dash, that is submerged unit weight. Okay, so there are multiple site conditions, multiple types of site conditions. There are, specifically speaking, 4 cases. So based on the type or based on the case, this equation will get slightly modified. Okay, so the moment you know what is the problem statement, if the problem statement is saying or it is suggesting that the site conditions are submerged, then you have to see that the gamma that is used will be submerged. Okay, this is the basic principle behind the entire changes that we are going to incorporate. So if the water table is located very close to the foundation, then the equation will require modifications. However, if the water is present at very large depths, okay, way much below than the foundation level, then we need not do any changes. Okay, so now, first rule, if dW, that is the depth of water, is greater than or equal to B. What is B? Width of the footing. Okay, That is, when the water table is at a distance below the foundation equal to the width of the foundation or greater than the width of the foundation, then there is no water table correction for overburden or beneath the footing. What is the meaning of this first statement? dW, that is the depth of water table below the foundation. So now over here, if just scroll down, if this is my foundation level dF, so if this is my foundation level, what you can see in dotted line, okay, and the water table is way much below. How much below? So if the width is B, let's say the width is around 2.5 meters and the foundation is 2.5 meters or more below the foundation level, then we need not apply any modifications. However, if the water table is little closer to the foundation level, then you will have to incorporate the changes. Okay? See, the corrections are primarily in these two terms. Okay, I've just rewritten the same equation down. In the second term and the third term, because gamma unit weight appears in the second and third term. Okay, this second term is basically talking about overburden. Okay, the second term, gamma into dF into input, is basically depicting the overburden conditions. What do you mean by overburden? The soil above the foundation level. Okay, so this term, this gamma will change based on the soil conditions above the foundation level. This third term is basically talking about the soil conditions below the foundation level. Okay, so if this soil, whatever is above the foundation level, is getting moistened or it's getting submerged, then this particular term, the second term will change. If the soil below the foundation is getting submerged, then the third term will change. Is that understood? It's very simple. Okay. The second thing that you need to take care of is a lot of problems when the site conditions are submerged. In your solution, you may see instead of gamma dash, okay, you may see gamma sat by 2. As a thumb rule, we are going to take gamma dash is equal to gamma sat by 2, half of the saturated unit weight. What is exact formula? Gamma dash is equal to gamma sat minus gamma W. But we will not do that. As a thumb rule, we will always take submerged density is half the saturated unit. So these are thumb rules which you will see again. So there is no need to get confused eventually when we will start solving problems. Okay. So now when you look at this particular diagram, 4 cases are very clearly shown here. Okay, that's why I decided to teach you all this particular concept from NPTEL. Very simple, very simplified cases. What is the case 1? Case 1 is when the groundwater table is right on top. Okay, water table is near the ground surface. Case 2 is what? Water table is below the ground surface but above the foundation level. Case 3, water table is at the foundation level. Case 4 is water table is way below. Okay, there cannot be any more cases. These are the 4 cases, and all these 4 cases, how are we going to tackle? Okay, now the first case, groundwater table is at the ground level. So what happens to the soil which is above the foundation level? If the water table is right on top, what happens to the soil which is above the foundation level? Obviously it is submerged. What happens to the soil which is below the foundation level? That also is going to be submerged. So in case of case 1, what will happen to this equation of yours is this second term and third term. You are directly going to replace the bulk unit weight by submerged unit weight. So use gamma dash for gamma dF NQ and 0.5 gamma V N gamma. Okay. Now case 2 is when water table is below the ground surface but above the foundation level. So now over here what we are going to do is we are going to introduce the concept of effective stress. Okay, now what is changing here? The overburden conditions are changing. What about the soil which is below the footing, below the foundation level? It's going to be submerged. So what is going to be a third term? Third term is going to be gamma dash. That is very clear. Now how are we going to tackle this partly submerged and partly non-submerged soil? So over here we are introducing sigma dash. What is sigma dash? We have studied this before. It stands for effective stress, which is given by sigma minus 0. What is sigma? Sigma will be unit weight of the soil into depth of the foundation. So whatever is the depth of the foundation, that into unit weight will give you sigma. And what will be U? U will be given by gamma W into HW. So what will be HW? It's not marked here. HW will be from this dotted line to the foundation level. Is that understood? Okay. So when there is the soil in the overburden is partly submerged, partly not, we are going to introduce sigma dash concept, which is equal to gamma into df minus gamma w into hw, where hw is the height of water above the foundation level. Okay, and for the third term, as I have already told you, you directly replace gamma by gamma dash. Now let's have a look at case 3. What is case 3? When the water table is at the foundation level. So if the water table is at the foundation level, what will happen to the soil in the overburden? Obviously it's not going to be affected. You continue using this gamma into df into nq term, right? But what about the third term? Third term will be gamma will be replaced by gamma dash. Is this very clear? So when water table is at the base of the footing, there is no correction to the overburden. But beneath the footing, the third term, 0.5 gamma b into n gamma, submerged unit weight will be considered. Excuse my typographical, the spelling is not wrong. Right? So use gamma for gamma d nq and gamma dash for 0.5 b gamma n gamma. Right? Now let's go to the case 4. What is case 4? Case 4 is when the water table is way below. So when the water table is way below, you will use directly obviously gamma for the second term and gamma for the third term. Okay, but there is a specific case here, that is in case of cohesive soil. Now if you realize, I have used here in granular soils, the presence of water in the soil can substantially reduce the bearing capacity. So all this what I have spoken is the effect is very much enhanced, okay, very much allowed when it is granular soil. What happens in case of cohesive soil? Okay, so this is a special case. Actually, this is not the fourth case, but comes under that category. So if the soil conditions are very cohesive, okay, then for short term or end of the construction condition, we use whatever. It's not necessary Kempton's analysis. Any, let's say Karzaghi's equation if we use, then the equation gets slightly modified. Why I specifically mentions Kempton's or Mayerhofs, you can even call this as Mayerhofs analysis. This NC value for, when I say cohesive soil, what happens to phi value? Phi becomes 0, right? So for phi 0, NC value, NQ value, N gamma, these are calculated. Yes, so these NC value and NQ value, as per Mayerhofs analysis, for phi is equal to 0, NC value is 5.14, NQ is 1, N gamma is 0. If you try to find out as per Karzaghi's analysis, then this value NC is 5.7. Okay, then if you go by IS code, again it is 5.4. So these are being used over here. Okay, I have mentioned majority of the cases this NC value is 5.14, NQ is 1 and N gamma is 0. and the equation gets further modified into QF is equal to 5.14C gamma dl. This is a special case. Okay, now I want to post a question for you all. For clay soil, QF doesn't depend on V. Justify. And second is, net ultimate bearing capacity is unaffected by the width, okay, by the rise of the water table. Okay, the net ultimate bearing capacity is unaffected by rise of the water table in case of clay soil. Justify. Alright, see you all next time. Take care.